Okay, today we go into details about the Quasi-Newton method. So recall the Quasi-Newton method was is presented in the following way. Right? We updated xk to xk plus 1 by subtracting this. So essentially, we're using this negative hk gk as the search direction instead of just a negative gk. And this h is a matrix we want to construct to approximate the inverse of the Hessian in the Newton's method. Right? So that's the purpose, or that's the general framework for the Quasi-Newton method. Okay, so again, we are going to talk about the Quasi-Newton method applied to the quadratic functions and the non-quadratic function or general functions. For quadratic functions, the function is given by, use a different color here. It's given by half x transpose qx minus b transpose x. Okay. So for this type of function, we know the gradient is qx minus b, and that the Hessian is just the Q matrix. Okay. For this quadratic function, we know the gradient. If you take the subtract the gradient gk plus 1 gk, right? This is the gradient of f at xk plus 1, gradient f at xk. You subtract this, then this is essentially just qxk plus 1 minus b minus this gk is just qxk minus b. So you cancel the b and you have just this. You just have this. Okay. Now let's use a shortcut notation because we don't want to write this kind of thing all the way along. We use this delta xk to denote the difference between xk plus 1 and xk. So this is basically like you move forward one step from xk to x plus 1, k plus 1, and this vector denotes the difference between these two vectors. And similarly, the delta gk denotes the difference for the gk. Okay, so one just denotes the forward. It's like the forward step size between the two. So it goes from gk to gk plus 1. So it's like this is gk, this is gk plus 1. So you move from gk to gk plus 1, and this is called delta gk. So this vector is denoted by delta gk. All right, so if we use this notation, then this equation just becomes this. It becomes this one. Okay, and if the q is positive definite, then we can multiply q inverse on both sides, and that will just become this. Okay, so recall that hk in the Quasi-Newton's method is trying to approximate the inverse of the Hessian. Okay, it's trying to approximate the inverse of the Hessian, and we know the Hessian is just q, constant q. And if you want to approximate the inverse of the Hessian, that means we want to use the hk. Again, the hk here denotes the matrix we want to use to approximate the inverse of the Hessian, and this h superscript k means the actual Hessian of the matrix of the function, which is constant if f is a quadratic function. Okay, so we're using this hk to approximate the Hessian. That means we want to replace this one by the hk. Okay, and if it's replacing the q inverse by hk, then at least the hk, when we multiply or we substitute q inverse by hk, we should still have this equation. So that's why for the Quasi-Newton's method, what do we really want? What do we need to require is that this hk delta gk is equal to delta xk. Okay, so we want to design the hk here in the Quasi-Newton's method such that this equation holds. And actually we want a little bit more than that, as we will show soon later. Okay, so now let's compare the Quasi-Newton's method and the Newton's method. The Newton's method for quadratic function is implemented in this way. Right? And this is the inverse of the Hessian, and this is the gradient. And for Quasi-Newton's method, we replace approximate the inverse of the Hessian by some HK matrix, and that's the Quasi-Newton method. And as I just mentioned, we want to obtain the HK matrix such that it satisfies this one. Okay, and but remember that this Q, if I have the Q here, it actually works for all the delta GK, delta XK. It works for all these ones. Okay, for K from 0 to 1 to 2 and to all the for all the Ks. But here, this is only one of the HK. For the next iteration, this HK will change. And so what we want for this HK is that when we have the HK, at least it works, or this equation holds for all the K, for all this K less than equal to the one I'm going to have here. So let me just directly go express this equation for requirement of HK. So we want this sequence of HK matrix to satisfy this property. So it is not just the HK plus 1 multiplied to delta G, not just for the I equals to K, but for all the I less than or equal to K. I want this to hold for every K. So that means for each iteration K, the new matrix HK plus 1 I'm going to compute should satisfy this equality for all the i's less than or equal to K. Okay, that means for all the deltas I computed so far, I want this HK plus 1 to be perpendicular to that. So if I write this in the following way, remember that in the first iteration I will get G0. Remember that this is just G1 minus G0. And on the right hand side, I have delta x0, which is just x1 plus minus x0. So I want this h1 equals to this. Okay, I want my h1 to satisfy this. Okay, and for h2, it does not only satisfy that the delta G0 equals to delta x0, but also satisfy delta G1 equals to delta x1. That's my requirement for H2. So it actually needs to satisfy two of those equations. And then for H3, it needs to satisfy all of them. So that means if I have, so let me put it in this way. So generally I should have this. I have this delta G0, delta x0. So they are not equal yet. I need to multiply the h on the left to get this to equal. But first write this down. So I need my hk plus 1 to satisfy all these k plus 1 equations. Okay, let me just erase this. Okay, so this is for h1, and this 2 is for h2. But for hk plus 1, I need all these m plus 1 equations to hold. Okay, that's my requirement for the HI construct. So we have a stronger condition, or stronger properties for HK plus 1 to satisfy. Okay, so for quadratic functions, these are the actually the definition of Quasi-Newton method, because there are different ways to construct this HK matrices. As long as the HK matrix we construct it in this way satisfy the properties I'm showing here, then we call it the Quasi-Newton's method. Okay, that's the definition for Quasi-Newton's method. Okay, now recall that if I'm going to do this, I'm going to have this HK satisfying this property for each iteration, then what happens after we finish the nth iteration? At the nth iteration, we were going to get the Hn, and that is supposed to be the Hn is supposed to satisfy all these equations for k equals 0, 1 up to n minus 1. Okay, and so the Hn should satisfy all these n equations, and that means if I put these vectors as columns in the matrix, then I put this vector as the first column here, this vector second column, up to this one, which is the last column here. So I will have the HK times, Hn times this matrix, and on the right hand side I will align these vectors as columns here in the same order. Then what I will get is this. This is my HK, which is a square matrix, n by n square matrix. And then this delta G will form another n by n matrix because there are n columns and each one is a n-dimensional vector. And on the right hand side, I have another n by n matrix. Okay, so that is what this equation is. And now imagine that, assuming that this delta G matrix is invertible, that means this matrix here is invertible. Then I can take the inverse. I can multiply the inverse of this matrix on both sides. Okay, a right multiplication. So it means I multiply the inverse of this matrix, and also the same inverse I need to multiply to this matrix, and then these two will cancel, and then I will just get HK equals to this, right? Because on the left I only have the Hn. On the left I have the Hn. On the right I have this matrix. Okay, so that is what happens for Hn. Okay, so on the other hand, I can also show that because the Q satisfies the Q inverse satisfies the same property. If I replace this by Q inverse, that's always true for quadratic functions, right? That's always true. So I can do the same thing. I can put Q inverse here, and I can put the columns, the delta Gns as the columns, and the delta X as the columns as well here. Then this, you compare these two. One is here, and the one is here. You can see that the same, they are the same, except that the Hn is becomes the Q inverse. Okay, and again, as I said, if the G matrix on the left is invertible, then I can multiply the inverse of it on both sides, and what I will get is Hn equals to Q inverse, because they are both equal to this matrix times this inverse of this matrix. Okay, so you just compare this, you can easily get Hn equals to Q inverse. Well, what we're trying to say here is, if we can guarantee the Quasi-Newton property for the HK, then after n iterations, the Hn matrix we get is actually the Q inverse. It's actually the Q inverse. And then let's say that we can do one more iteration, and the next iteration we're going to do is update xn to xn plus 1. And here we're going to use the Hn, and the Hn is shown to be the Q inverse. Okay, if we assume this is invertible, then this Hn is just the Q inverse. And if this is the Q inverse, that means we're actually doing the Newton's step, right, or the Newton's update. And we know that for Newton's method, when it is applied to quadratic function, we will get to the true solution x star within just one step. And that means the xn plus 1 must be the minimizer of the quadratic function. Okay, And this also means that if we can guarantee this property of the Quasi-Newton's method, then after n iterations, we must be able to get the minimizer, the true minimizer. Okay, so now the question is, how do we really guarantee that, right? Guarantee that property. Okay, so in summary of what we have done so far, we said that the Quasi-Newton's method will set the search direction dk to hk times the negative gradient. So the hk is something that we try to determine for the Quasi-Newton method. And once we have this, we can do a length search, just like in gradient descent method or the conjugate gradient method applied to non-quadratic functions. We can apply that and find a step size alpha k. And then once we have the alpha k, we will have this. Sorry, this should be alpha k. Once we have alpha k, we'll update the xk to the next one. Okay, so this should be xk here. Okay, so that's the what we need to do for each iteration of the Quasi-Newton's method. And the most tricky part is to generate those sequence of matrices in each iteration along with your xk's, so that the hk plus 1 or for each k, the hk plus 1 makes this equalities hold. And that is the requirement for the Quasi-Newton's method. Okay. Now, before we actually dig into a specific choice of the H matrix, or how do we choose this H matrix, let's first consider a property of the Quasi-Newton method. Suppose this property holds in the Quasi-Newton method. What we'll get is a very nice property. So in summary, if we can guarantee this property of the H, these dk vectors are actually Q conjugate to each other. Okay, and that is a very nice. Recall that what we did in the conjugated gradient method. The key is to construct this conjugated gradient direction, Q conjugate directions. And if we're using the Q conjugate directions as a search direction, we can guarantee convergence to the minimizer within n steps for quadratic functions. Okay, and the Quasi-Newton's method actually has the same property here. Okay, actually can guarantee the same property. So let's recall let's say what the theorem says. Consider we have a Quasi-Newton's algorithm that is applied to a quadratic function with positive definite matrix Q. So I should say this quadratic, always assume this is positive definite. Then, and also that the hk satisfies the Quasi-Newton's property. hk plus 1 is multiplied to delta g I is equal to delta xi for all the I less than or equal to k. And then the D matrix, D vectors are actually Q conjugate. And if you can do this, then the D vectors we construct are actually Q conjugate. Okay, so still recall what is Q conjugate. We say two vectors di, dj are Q conjugate if di, dj, I will say it in this way, d0, d1 through dn, it should be n minus 1, should be n minus 1, are Q conjugate if diq dj is equal to 0 for all the I not equal to j. Right? That's the property of that's the definition for Q conjugate vectors. So we're going to show this for the Quasi-Newton method. Again, we're going to show this by induction. We first show that D1 is Q conjugate Q conjugated with D0. Then that is trivial to show. That would be trivial to show. If we start with the let's see, remember that we get the D0. Okay, before we move on, I actually want to add one more comment to this theorem. Not only just that the D vectors are Q conjugate, but we also have something similar to the conjugate gradient method, which says that the GK plus 1 is perpendicular to the DJs for all the J from 0 to K. Okay, and this is due to the way we chose this line search function. Choose the step size. For quadratic functions, as we recall, the quadratic functions, we just repeat. And then suppose we already get the xk and also the dk. We know that the hk plus 1 is equal to xk plus alpha k dk. And recall how we got this alpha k. Alpha k is the steeply descent step size. And for quadratic function, this step size should be chosen to minimize the f of xk plus alpha dk. Right? And to minimize this, we know that we can just take the gradient derivative with respect to alpha and set to 0. By taking the derivative with respect to alpha, we'll get this times dk transpose dk. This should be equal to 0 if we really reach the minimizer, which means here, if I'm using the alpha k, I'll get the minimizer, so that's why this is true. And this part is the gk plus 1. Okay? So the gk plus 1 is perpendicular to the dk's, so that's 1. And using this, at least in the first iteration, we know that the G1 should be perpendicular to the D0. And actually for each iteration, the way we chose this alpha k will make this GK plus 1 perpendicular to the DK. Okay, but if the DKs are also Q conjugate directions, that means for each iteration, we get we obtain the update of x using the Q conjugate directions, then the GK plus 1 will be perpendicular to the DJ for all the j less than or equal to k. And that is the thing that we proved in the for the conjugated gradient method. But that is all based on that these are Q conjugate directions. So what we can do here is that when we apply the induction, we imagine that when we apply the induction, we will assume that the dj or the dk is Q conjugate to all the previous dj's for j less than or equal to k minus 1. This is our induction hypothesis if we want to prove this theorem. And then when we want to use this to prove the next one. So, or I should say here the induction hypothesis is that the d0 through, suppose that d0 through dk are Q conjugate. Okay, and then we want to prove, we need to show that dk plus 1 transpose q dj is equal to 0 for all the j less than or equal to k. And also from here, we can also prove that the gk plus 1 is perpendicular to the dj for all the j less than or equal to k. Okay, but if we can do this, actually in the induction hypothesis, we can also have this. We can assume that this gk transpose dj is also equal to 0 for all the j less than or equal to k minus 1. So we can have both of them and then use them to prove the last line. Here, that would be the strategy we can use. But for this part, from this part to this part, this is exactly the same as in the conjugate gradient method. So I will not repeat that. So we just assume that once we just need to prove that this Q conjugate implies that, then this implies this will be automatic. Okay, so in the first iteration, I will say that this is easy to check because it's just because for the first iteration we can easily check the G1 is perpendicular to G0, which is just one of them, and then we can, using this, we can prove that this property will hold for k equals to 0, and that is the starting point of the induction. So that's why I'm saying that it is trivial to show for the case k equals to 0, because when k equals to 0, let me write it here, I know that the G1 is perpendicular to G0 because of the way we chose the alpha 0. This is because the alpha 0 was chosen to be negative G0 transpose D0 divided by D0 transpose Q D0. Okay, the steeply descent step size. Okay, and also in the first iteration, also know that D0 is equal to negative G0. Okay, and from this property, we can show that D1 is Q conjugate with D0. Okay, this will be equal to 0. Okay, and why is that? It is because the x1, recall that x1 is equal to x0 plus alpha d0, right? So if I multiply q on both sides and subtract b, I will get qx1 minus b equals to qx0 minus b plus alpha 0 d0 q d0, right? And then this, recall that this is the G0 G1, this part is the G0. So that means G1 minus G0 equals to alpha 0 Q D0. Okay, but also recall that the D1, the delta G0 I can get that this is just the delta G0, because I move the G0 to the left, then G1 minus G0 is delta G0, that's equal to alpha 0 Q D0. Okay, and then the Q D0, it will be just equal to delta G0 divided by alpha 0. Okay, that is the thing that I'm going to plug in here. But the steps will be the same as what I'm going to show below. So I will just jump to the general case below. So what I'm saying that it's trivial to show in the first step that the G1 transpose D0 is equal to 0. Okay, and then, so that's what I can show in the first step to show this. To show this. And then we can use the property of this HK matrix to show that the dk plus 1 will be Q conjugate with all the previous DJs. So our DIs I is less than or equal to K. Okay, so to show that, let's look at this product. We want to show this is equal to 0 for all the I less than or equal to K. Okay, the first thing we can do is that recall the definition for the descent direction. The Quasi-Newton's method requires this to be negative HK plus 1 GK plus 1. That's our Quasi-Newton's method. So that's why we just replace this by negative of this. Okay, and that's for this, and I just put the transpose inside. I will put the GK plus 1 transpose and the HK plus 1 transpose, but the HK, we also set the H to be a symmetric matrix, so that is the same as itself. And then the QDI. The QDI is equal to a similar thing as we showed earlier. The DI plus 1 was obtained by XI plus 1 was obtained by XI plus alpha I DI. Right? So that's why when I multiply Q on both sides, or I first move this XI to the left, I will get delta XI equals to alpha I DI. And then I multiply Q on both sides. I will have this. Okay, and that's why when I divide both sides by alpha I, I'll get this Q di. Okay. Okay, so that this part implies this will make this term become this. Okay. Now recall that the Q delta xi is always just equal to delta gi. Right? That's what we have been showing before. Q delta xi, xk is always equal to delta gk. So I can replace this Q delta xi by delta gi. Okay, and then recall the property of the HK. We'll assume that or HK satisfies the Quasi-Newton's property. So the HK plus 1 multiplied to delta gi, where I is less than or equal to k, will always give us the delta xi. Okay, so that's why this part will be just the delta xi. It's this. But the delta xi divided by alpha I is, what you call here, the delta xi divided by alpha I will be just the di. So that's why we'll have just this di. Okay, and then we reduce to this. The gk plus 1 is transpose di. By the induction hypothesis, if we obtain all the di's as conjugate Q conjugate directions up to the kth iteration, then this gk plus 1 will be perpendicular to all the di's for I less than or equal to k. That is the property we mentioned for Q conjugated method, for conjugated gradient method. If these di's are Q conjugate up to k, then this will be perpendicular to that. And in addition to together with the property of this HK, which converts this thing to delta xi, we can show that the dk plus 1 q di is just this, and this is equal to 0. And this proves the claim, because the induction can continue to go on. So in summary, what we can prove so far is that assuming that this is true, then we can immediately apply this one here to the same logic here. Then we'll get, say we have a g1 d0, and we can just set k equals to 0 here. K equals to 0 here. Sorry, this I will be just can only be 0 because k is equal to 0. So I less than equal to 0, I has to be 0. And this is just 0. So it's just d1 q d0 is equal to negative g1 d0, which is excuse me, which is 0, as we show in the first step. And then we assume, since we always assume this is true, we want to continue. And for general dk plus 1 transpose times q di, we can show that this is equal to this. But because that we have assumed that the di's are all q conjugate so far, I mean d0s from d0 to dk, they are all q conjugate. The next dk plus 1 must be perpendicular to all the previous ones, all the previous di's. So that makes this always equal to 0. And from this derivation, when we go back to here, using the fact that using this property of the hk, which converts this, which makes these two things equal, we can go back from this to that. And this equal to 0 just means that this is equal to 0. And this is what we wanted to prove. We want, which is that the dk plus 1 will also q conjugate to all the previous ones. And this is finishes the proof. Okay. So what this theorem actually says is that if we have the Quasi-Newton's property for the H matrix, then the Quasi-Newton's method is actually a conjugated direction method. It's not a conjugated gradient method yet, but it is generating Q conjugated directions along the way, although it is different from the way we generate those directions in the conjugated gradient method. But it is still a conjugate direction method. That means the directions are actually Q conjugate. And in this sense, the algorithm should converge after n steps for quadratic functions, because this is another way to verify that the Quasi-Newton method can give us a convergence within a finite set. Previously, we showed that it's a little bit shaky that we're assuming this matrix is invertible, so we can multiply this inverse of this matrix on both sides to show that the Hn is equal to Q. After n iterations, the Hn is equal to Q inverse, or here. But this theorem proves from a different approach, proves that this is actually true for Quasi-Newton's method. So the only thing that we need to guarantee is this property, right? The HK satisfies this property. Okay, now I'm going to introduce 3 algorithms developed in the history for constructing this H matrix. The first one is called rank 1 correction. The rank 1 correction method, as you can see from the name, is that we're going to update the HK matrix to HK plus 1 matrix by adding a rank 1 matrix. So this rank 1 matrix is written as some scalar ak times the vector zk and the transpose of this vector. So here, this is a column vector for zk and the same vector, but I put it transpose, which is a row vector, and the product of these two gives us a matrix, and that is a rank 1 matrix. Sometimes it's also called the outer product of the vector zk. Okay, and this A is just a scalar. Okay, so now this will be our rank 1 update or rank 1 correction formula. And the question is how should we choose this AK and how should we choose this ZK vector? Okay. Okay. Remember that this is really artificial. It sounds really artificial. We just add this thing to the HK and we hope that HK plus 1, this HK we generated will satisfy the Quasi-Newton's condition. But let's say this is the case. Let's see if we can actually find this ZK and AK. Okay, to find this ZK AK, let's say what the properties they need to satisfy. We need to guarantee that the new HK plus 1 is, when we multiply this to delta Gi, it should be equal to delta Xi for all the I less than equal to K. This is the property. This is a property that is this rank 1 matrix should satisfy. Okay, so apparently, as we said before, this actually involves k plus 1 equations, because this I needs to be any one between 0 and k. So there are k plus 1 of these equations that we need to satisfy. And so at least you need to satisfy the last one, right? Which is for the case I equals to k. So we need to first choose this AKZK such that the HK plus 1 satisfies this equation for I equals to k. But not only just I equals to k, but also other ones. But at least I equals to k. Okay, so for I equals to k, as we said, the delta HXK should be equal to this. And then the HK plus 1 was updated from HK by adding this rank 1 matrix, so I replace it back. Okay, so this is the matrix. And now I put this delta GK inside. I'll have the HK times this plus this. Okay, and I need to make sure that I know that my ZK needs to satisfy this equation. At least needs to satisfy this equation. Okay, since it satisfies this, recall that here, when I multiply this row vector to this column vector, or I combine these two together, it's a row vector here and a column vector. So I will get the inner product of them. That it will be just a scalar. So what I have in the parentheses here is just a scalar. And now I have another scalar here. So I don't need to worry about this, just two scalars multiplied to the zk. So later on, I'm going to move this to the left and divide both sides by this scalar. And that is my zk. Okay, that's my zk, what zk should satisfy. Well, if zk is this, then I need to remember that I actually added this AK, ZK transpose to this HK to obtain the HK plus 1. Okay, and if ZK is this, I will just need to put them inside, and I will simplify this into this formula. Okay, so you can do that simply by plugging this ZK into these two, and you get this ZK. Okay, it's not that complicated as long as you realize that this will be just a vector on the numerator, this is a scalar on the denominator. Okay, so the ZK transpose is just the outer product of the numerator, which gives us a rank 1 matrix, and a scalar, the square of the denominator, which gives me another scalar on the denominator here. Okay, we have done this kind of artificial transformations, but it didn't really help us to get what is ZK and AK because it's still here, right? They're still here. To get rid of them, let's multiply the delta GK transpose on both sides of this equation above. So I'm going to multiply the delta GK transpose, which is a row vector. So now both sides are matrices. This is a matrix, this is a matrix, and here this whole thing here is just another rank 1 matrix. So I'm going to multiply a row vector on both sides, which is this vector. Oh, sorry, I'm going to multiply this this vector to this one, to both sides of this. So this is the one, this is the previous one we have. We move this to the left, and then we multiply the delta GI or delta GK on both sides. So this is the equation I just have from the previous slide. When I multiply the delta GK transpose, the left-hand side is this. In the right-hand side, you call that this right-hand side, but these two are both scalars. Only this is a column vector. But when I multiply a row vector from left to the left multiplying a row vector to this, I will get a scalar. And that is the same scalar as this one, which is the inner product of the two vectors. So that's why I have just a square of the inner product of these two vectors. Okay, Now, we don't really need to know what is AK and ZK because I know that my rank 1 update should be this with this as the denominator. But now the denominator is shown to be this, right? Because this is the denominator, same denominator here. And I know that they are equal to this. So I just replaced it. And now I will get the final update equation. And this is called rank 1 correction. The reason that we can just directly use this is because everything on the right hand side are available to us. So everything on the right hand side is available. When we do each iteration, we know each iteration of the Quasi-Newton method, we can compute the xk plus 1. And once we have xk plus 1 and xk, we know the delta xk. And when we multiply q on both sides, we will get the delta gk. So we know all of them. We know the delta, stay here. We know the delta xk, we know the delta gk, and the hk is from the previous iteration, which is known. So everything on the right hand side can be computed. And that's how we get the hk plus 1. And once we have the hk plus 1, we can use it to update the descent direction. And just let the iteration go on. Okay, so that is, although initially we try to update HK matrix using this ZK vector, but it turns out that we don't really need to find out what this ZK vector is. But no matter what it is, in order to make at least the last one, at least to make this one hold for I equals to k, it is already determined that this rank 1 matrix needs to be in this form. Okay. Now we just showed this rank 1 matrix update so that it satisfies this. But recall that for the Quasi-Newton's method, we actually need this one to hold for all the I less than equal to k. We just showed that it is true for I equals to k. Also need to show it is true for I less than k. And this is the theorem I'm going to show next. It verifies that this is actually true for all the I less than k as well. Okay, to show that, let's show that this is as we showed that by the way of rank 1 update formula, the hk plus 1 is guaranteed to satisfy this equation. But we want to show this is also true if we have the I here, where I is less than k. Okay, so to show that, we just multiply the hk plus 1 to delta gi. Okay. Okay, here we're going to do the induction as well. So suppose that by using the rank 1, so induction hypothesis, assume that the hk, say hk delta gi is equal to delta xi for all the I less than or equal to k minus 1. This is our induction hypothesis. Now we need to show the hk plus 1 times delta gi is equal to delta xi for all the I less than equal to k. But we already showed the case for I equals to k. So again, here we just need to show this. Okay. So to show this, hk plus 1 times delta gi. Recall the formula for the rank 1 update. The hk plus 1 is just this. Okay. Now put this and this together, because I is less than or equal to k plus k minus 1. So assume, according to the induction hypothesis, the product of these two is just the delta xi. So this 2 gives us the delta xi. And next, multiply this whole thing to delta gi. But this is a row vector, column vector, so put them together. That will just give us this part. So this becomes a scalar. This is again the scalar we had, and this is a column vector. Okay, now let's just look at what the scalar is. The scalar, when I multiply these two vectors as the inner product of the two vectors, I first check what happens when I multiply this one to this. So I multiply these two together, I have this. Right? This is just this part. And that turns out to be, I put the transpose to inside of this, I will have just a reverse zero order. HK is symmetric, so it's just this. And now, record the HK, again using the induction hypothesis, this is just equal to delta xi. So this part is just a delta xi. Okay, and recall that the delta xi is going to be here, and delta gk is q times delta xk. You always recall that for quadratic function, delta gk is equal to q times delta xk. That's why this transpose becomes this. So from here to here, we'll use delta gk equals to q delta xk. That's why we have that. Right? When I put transpose this, and it's the same as taking the transpose this, and that's just the transpose of this times the transpose of this, and which is the q itself, since the q is symmetric. Okay, now I'll get that. And then I move, what I'm trying to do here is just get this q, but I'm going to put it together with this delta xi, because this is just equal to delta gi. Okay, so what we showed is this is equal to delta xk delta gi. But here we have delta xk delta gi. And what we showed, this is equal to this times this, and they are cancelled. So that means the minus means they are cancelled. So that means this whole thing is just a 0. And that 0 means that the second term is completely gone. So that's why delta k plus 1 times delta gi is just equal to this. So that's how we show that this is also true for I less than k, less than or equal to k minus 1. So together with the previous, with the one that with this, we can complete the induction. Okay, so this finishes the proof that the rank 1 update actually guarantees the HKs to satisfy the Quasi-Newton's update rule. Okay, the HK plus 1 is times delta xi is actually delta gi is actually equal to delta xi for all the I less than equal to k. Okay, so that's the rank 1 matrix. I think it looks a little bit magic that everything just cancels out so nicely, and we end up with this very nice rank 1 updated formula. And in practice, it does works, but in some cases, it has an issue. There are two issues I'm going to put here. The first one is that recall the updated rule for the rank 1 update matrix. So this is rank 1 update. The issue with this term is that it's not necessarily adding these two matrices together is not necessarily giving us a positive definite matrix. Even if this one is positive definite, adding this one, this is something that we don't know. We don't actually know the behavior. So it could happen that the HK plus 1 is not positive definite, and in that case, we may not get a decent direction. This one may not be a decent direction. The second issue is that in the rank 1 update formula, this denominator after certain iterations, it could be very close to 0. When it is close to 0, dividing it can make this computation not very stable, because there will always be some numerical stability issue during the actual computations. So that is another kind of drawback of rank 1 update rule. And that's why there are some other methods developed to overcome the issue. So for example, there's the so-called Dfp algorithm, or Dfp formula, because it's developed by the 3 people, Davidson, Fletcher, and Powell. So that's the initial of these 3 guys. It's called Dfp algorithm. And they said that the HK can be updated by using this formula, where this is the existing or the current HK. This is the ratio. Again, this is a denominator. It's a scalar on the denominator. It's the column vector and row vector here. And this is again a column vector and row vector, because each one is a matrix times a column vector. So you will get a column vector, and same column vector here. We get a rank 1 matrix. The denominator is again a scalar. So I said this will be the update rule. And it actually can be shown that this is also a quasi-Newton's method by this choice. By this choice, it's still a quasi-Newton's method. And to show that, we're again going to do this by induction. So it's trivial it's similarly as before, it's trivial for k equals 0, and assume the induction hypothesis, which means that HK does satisfy that inequality, satisfy that equation for I less than or equal to k minus 1. And we're going to show that this is true for all the I less than or equal to k. Okay, we can directly show when we multiply this. We can directly show this HK plus 1 times delta GK equals to delta XK, and that can be shown by just directly multiplying this side by delta GK, and then I will need to multiply this whole thing by delta GK. And let's see what happens. If I do this, then I'll have the HK delta GK, okay, and then add, this will be, on the numerator I'll have delta XK, and the delta XK transpose times this. I'm going to have this multiplied to this. So when I multiply this whole thing to this, it's just that this is multiplied to that. It's row vector and column vector, and that is the same inner product as the bottom. So they will be cancelled, right? So when I multiply this and then this, the inner product of these two is just the same as the inner product here. So they are cancelled. Now what I end up with for the this term will be just the delta XK. Okay, and then the next one, I will need to multiply this with this delta GK. But recall that I just need to make inner product of this with this, and that is the same one as the bottom here. So they will be just cancelled. So I only have this part here, this circled one here, and that circled one is just the negative HK delta GK. Okay, and you can see these two are cancelled and won't have the delta XK. So that's why this quasi-Newton's rule at least is satisfied for I equals to k. But what they need to do is also show that it works for I less than k. So what I just did is this is true for I equals to k. For I less than k, what I have is just do this computation and applying the Dfp update rule, change the HK to HK plus 1 to this, and also this is the second part, this is the third part, right? And let's see what happens when I multiply delta GI on the right. Okay, I know I get this. And now, because we during the induction hypothesis we said that the HK satisfies this, so then the DIs we generated along the way are Q conjugate. So the D0 to dk, they're all Q conjugate. We're going to use this fact to show that this side is just is nothing but just delta xi. Okay, so remember that the delta xk times delta gi, they're just the delta gi is just replaced by this, right? And recall that for delta xk, is equal to alpha k delta q dk, because this left hand side is just xk plus 1 minus xk, right? So that's why we have this. The dk is just equal to the delta xk is just equal to alpha k dk. So I'm going to replace this by or this by alpha k dk, and this will be alpha I di, and that's why I end up with this. But since these vectors are Q conjugate, so I know this is just equal to 0. So whenever we see this delta xk delta gi, for I less than k, we know this is 0. So that means this is just 0. Okay, and similarly, we can show that the delta gk transpose hk delta gi, this term is equal to, recall that the hk satisfies the induction hypothesis, so this part is just the delta xi. Well, the delta xi is equal to alpha I di, so this term is just the alpha I di. Oh, sorry, here should be, yeah, this should be alpha I di. We actually get back to the previous one. Let me just maybe just show that would be easier. This delta gk is just equal to the q times delta xk. Okay, and then if you have this, you can see that this is nothing but, this term is nothing but delta xk transpose q delta xi, and that is just this same thing here, and that is supposed to be 0. This will be equal to 0. So that means this term will be equal to 0 as well. So this is 0, this is 0, so all these two terms are just gone. Okay, and then I'll just have this equal to the hk delta gi for I less than k. But for I less than equal to k, I know this, less than k, I know this is just equal to delta xi. And that completes the proof because this is equal to delta xi. Okay, so this shows that the DFP update rule also is a Quasi-Newton's method.